an Astronomy.fm original program. It's time for York Universe, a co-production of the Observatory of York University, Toronto, and the Voice of Astronomy. AFM Radio, AFM Radio, AFM Radio, AFM Radio.
Hello and welcome to York Universe, the astronomy and astrophysics program written and presented by students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening. I'm Elena Hyde, and I'm joined tonight by Quentin Wayrich. Say hello, Quentin.
Hello, everybody.
It's awesome to be here tonight, this reasonably clear Monday. We are broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. This is, in fact, Science Night in Canada, in case you didn't know. The lineup is all Canadian, starting with ourselves, York Universe, and then on to Western World's Quirks and Quarks and Science for the People. York Universe broadcasts every Monday night, except for holidays, so that does mean not next Monday, at 9 p.m. local Toronto time. And we actually have a wonderful archive as well, so if you have missed any of our previous broadcasts, or if you want to find out more about our online public viewing, hop on over to observatory.info.yorku.ca. For tonight, you can follow the links to OPV, online public viewing, and that will take you to a live YouTube chat where you can join our crew and chat about astronomy stuff and all kinds of fun things. You'll also find the archives, just one link up on OPV in case you want to catch on any of our previous episodes. Our broadcast is powered by and in partnership with Astronomy.fm, the voice of astronomy. If you have any questions or comments about our past shows or suggestions for future topics, you can email us at observe@yorku.ca. And of course, not to forget our wonderful social media team. You can always connect us with us on Twitter and Instagram at York Observatory and York U Observatory, respectively, and at Facebook at Allan Carswell OBS. All of our programs are free, but if you'd like to make a donation or buy a really cool coffee mug, see our website at observatory.info.yorku.ca. So we will be monitoring the chat room for questions over on YouTube, so feel free to hop over and say hi. And in the meantime, let's go ahead and get this wonderful Monday started. We have all kinds of fun facts from space and astronomy history to tell you about, but actually we're going to break it up a little bit today, and we're going to start with something, kind of unusual. You might have heard of our Astronomer in Residence program. Well, it's actually running right now. And Quentin, you are the Astronomer in Residence right now.
Yes, I am. I am broadcasting live from Killarney Provincial Park in Northern Ontario, just an hour outside of Sudbury, and it is a fantastic night. It is a little bit cloudy, but the moon is nice and it's getting full, and it's shining through the clouds. It looks absolutely gorgeous. So I'm having a fantastic time here.
It is actually a certified dark sky location, and the observatory at Killarney Park has been working with us here in Toronto for York Observatory to run this Astronomer in Residence program all summer. Quentin is the lucky last astronomer that we're sending up this summer. He'll be there until October 9th. I believe you have a few more shows running at the Park Observatory, Quentin?
Yes, so I have events planned for Wednesday, Friday, and Saturday. Wednesday and Friday, I'm going to be running stargazing events from the beach. I'm going to be bringing some planispheres out and pointing out planets and constellations to any interested members of the public. And on Friday, I am going to be doing a talk at the Killarney Provincial Park Amphitheatre. I'm going to be talking about the history of the Sudbury Basin, which is actually the third largest impact crater in the world. So if anybody in the audience right now is thinking maybe they'd like to go on a camping trip sometime this week, why not come on up to Killarney and you can see me.
That sounds amazing. And I have to say, having been there myself, if you get a chance to go out and look at those stars, the dark skies are absolutely incredible. And you might notice if you're looking up in the night sky, there's a faint, blurry, sort of streamy thing going overhead in Killarney that you can't see at all here in downtown Toronto. That is, in fact, the Milky Way galaxy. You can see it really, really well at that dark sky site. And I've even had people say that they can see naked eye the Andromeda Galaxy, which is a faint fuzzy object just to the side of the Great Square of Pegasus. And it's the only thing that you can see in the northern hemisphere with your naked eye that's not part of our galaxy. It's really cool. I can't possibly oversell it enough. So, and actually, we just had a giant festival out at Killarney Park, Stars Over Killarney, that has ended now, Quentin?
Yes, so Stars Over Killarney was this weekend. It started Friday night and went until Sunday morning. And what we were doing was each evening we were doing a big gathering. We had astronomers in from Sudbury and North Bay. They all brought their telescopes and they set them up in the observatory area. And all sorts of guests could come in and take a look through our telescopes and take a look through the telescopes of our visiting astronomers as well. Each night we would go through the planets, the superior planets, so Jupiter, Saturn, Uranus, Neptune, and Mars, and show them all on a screen. And I would provide little commentary on the planets and answer any questions from the crowd. But we also had events during the day. We've done solar observing events, usually starting at 2 p.m. And on Saturday, we had a keynote speaker, Dr. Gordon Osinski, who is a very celebrated planetary scientist. He's actually helped train astronauts to recognize geological features. And he talked a little bit about that research. We've been putting on lots of guided hikes. It's just been a great weekend, and I'm so glad that I was able to take part.
Absolutely. And if you weren't able to take part and you're now terribly, terribly jealous, there is some hope. Actually, we were able to pull live feed from the camera at Killarney Observatory through the eyepiece camera onto the YouTube channel, just like we do for online public viewing. We actually pulled that through just a couple days ago, and it's still on our YouTube channel as a recording. Now, there's no sound, it's just imaging, but you will see some very, very lovely pictures of the planet Jupiter, Saturn, Neptune, and Uranus, I believe. And in Jupiter really turns out very, very well. It just had its closest approach to Earth a week ago, 2 weeks ago, some number of days ago. And it is as lovely as you can imagine. You can make out the rings and all kinds of great details. So if you want to catch that stream, it has ended, but we did record it, and it's on our YouTube channel under the live stream area. So that's the York Allan I. Carswell Observatory YouTube, and that's also on the website. So lots of reasons to go to the website and check it out. We'll probably be working on a Teletube episode, maybe not this week, but next week, just to run through all of the fun stuff happening. And while this was going on, we actually had the same time Stars Over Killarney was being recorded, Nuit Blanche was happening here in Toronto, and somehow it all got scheduled onto the same day. So we actually had the York Allan I. Carswell Observatory, the atrium at the Allan I. Carswell Observatory, the Jeopardy game at the Allan I. Carswell Observatory, and the Killarney Park Observatory all running at the same time last Saturday. Very, very fun week for astronomy, and lots of great reasons to, as they say, look uppity. All right, so Killarney Provincial Park, definitely a destination. You heard it here probably a few times now, but we will be running this program again next year. It's been a wonderful success, and we all definitely wish Quentin the very best time until he has to leave on October 9th, I believe. So wonderful summer, and hopefully you get even more clear skies out there.
I really hope so. I've still yet to see the Northern Lights. A few people have said, in fact, I've seen pictures from some of the park staff here, especially as we approach the solar maximum, which I believe is happening in 2023 and 2024. We're getting more aurora activity, and we've seen the Northern Lights in the park a few times. Unfortunately, I haven't been able to witness them myself. So I'm really hoping in my final week I can catch a glimpse of those Northern Lights.
Oh, I wish you the very best of luck. I was just dying of jealousy. I went to the beach several times and couldn't see them. And the day after I left, someone posted on Twitter from the beach a wonderful Northern Lights shot. So as far as I know, the beach at Killarney Park is one of the best locations for Northern Lights viewing because of that clear, sort of almost to the horizon view. But yes, if you do get any pictures, please do share them because that is very exciting.
Absolutely. If I get any pictures, I'll be sure to put them in the blog.
And it is actually, as you say, we're going into a solar maximum. The sun is increasing in activity. So if you have a pinhole camera or some safe way to view the sun, there are more sunspots. And if you go to NASA SOHO or NASA Solar Observing, they'll show you what sunspots are currently out there. And you can actually watch, over the course of a few days, how they change their positions and move around. It's a very interesting, active sun right now, which is making it interesting for some satellites, I understand, but also really, really fun to be out at provincial parks. All right, so we could obviously stay on this topic for a long time, but we should probably get to a little bit of This Week in Space and Astronomy history. Quentin, I'm going to actually start off with you and have you do our first This Week in Space and Astronomy history fun fact.
All right. So 2 years and a week ago, on September 26, 2020, Comet 88P Howell reached perihelion in its most recent orbit. Howell, which was discovered in 1981, has a 5.5-year orbital period, and its next perihelion will occur on March 18, 2026. Comet Howell is the subject of a proposed research project called Comet Rendezvous Sample Acquisition, Investigation, and Return, or CORSAIR, which would send a probe to the comet capable of gathering samples and returning them to Earth for research. The aim of the project is to investigate the role of comets as ingredients for planets and life. If this mission sounds familiar to you, it's quite similar in concept to the Osiris-Rex mission, which successfully collected a sample from the asteroid Bennu in 2018. Osiris-Rex is actually due to return to Earth with its sample almost exactly a year from now, September 24th, 2023. So a year less a week. A team from NASA's Goddard Space Flight Center initially submitted the CORSAIR project as a candidate for the fourth mission of the New Frontiers program in 2017, which means if it had been selected, it would have been the follow-up mission to Osiris-Rex. However, in the end, the Dragonfly Titan probe was selected as the fourth mission of the New Frontiers program instead. That said, the project may be resubmitted to a future program call, so we may end up paying Comet Howell a visit at some point after all.
Amazing. And sample return missions are just so fun. And of course, we have had sample return from the moon several times, most recently, I believe by China. But asteroids and other planets and comets have all been challenging. We do get meteorites striking the Earth, so we get some samples from that. But if we're trying to figure out some of the big questions in astrobiology, in particular, the great origin of life question and the origin of life by non-living matter, is it possible to evolve from simple organic compounds, these kinds of chemical reactions and the materials that they need? Could they have come from comets? And that's been a question for a long time, actually. There's been the classic, was it 1952 or so, the Miller-Urey experiment showed those amino acids, the early sort of precursors for proteins were might have potentially had their origins in some cometary material. And so comets have been really interesting in astronomy for a lot of reasons. And of course, also they're very interesting historically, watching comets go by and get brighter in the sky. So this is a really fun one to watch. And I think that when that sample comes back, you will be hearing quite a lot of it in the news. So fingers and toes crossed for this mission.
Absolutely. I can't wait.
We'll have to, though. It's as the as the Artemis mission is demonstrating to us currently, patience is very much a virtue in space exploration. But yes, it is incredibly exciting times in astronomy right now. A lot of parts due to the work of all these missions that have been in the process for so long. That said, I'll go back to 2017, talking about missions that have been in the process for quite a while. October 3rd, 2017, the Nobel Prize for Physics was awarded for decisive contributions to the LIGO detector and the observation of gravitational waves. This was Rainier Weiss, Barry Barish, and Kip Thorne. And it was a really interesting Nobel Prize because this one and the LIGO consortium was, I think, one of the first really, really, really giant collaborations that got a lot of acknowledgement for the huge number of people and the incredible amount of time that it took for this to actually materialize. So it was decades and decades in the making, and the LIGO gravitational wave detector is a brilliant triumph of engineering and theoretical physics. But although construction began in 1994, it did not immediately have a success, and 21 years had to go by before all the efforts of not just Weiss, Thorne, and Barish, but the thousands of people who worked in and around this project finally paid off. And they actually had a detection of gravitational waves. It was an incredible point in history, in astronomy history. And it also really showcases the importance of I guess a bit of perseverance on science projects. You don't necessarily see immediate results on a lot of these projects because the engineering is so difficult. We had advances in computing, lasers, optics, and we've all seen how much better our cell phones have gotten in the last 21 years. And actually, this would be several years ago now. The miniaturization and precision that is now possible in optics and in laser physics is needed very, very badly if you're going to detect something as I won't say the word ethereal, but as difficult as gravitational waves. So the prize was awarded in October 3rd. So that's why I picked it as my sort of moment of history. It was, of course, awarded by the Royal Swedish Academy of Sciences in Stockholm, and it was actually split in an interesting way. So they picked these three people, and Weiss actually got half of the prize, and Barish and Thorne shared the other half. So the celebrations around this went quite a way for at least a year after this, because this was a detection that was not thought possible for quite some time. So in the 1970s, Weiss designed laser-based interferometers to detect gravitational waves. And gravitational waves have been predicted by Albert Einstein, but it's not a wave as you think of a wave. It's not a wave that moves through the air. It's not a wave that moves like light moves. It's a wave that is a fluctuation in the space-time of the universe. And that's as much detail as I'm going to get into for this broadcast. But if you're trying to detect something like this, it is absolutely crucial to have your instruments perfectly calibrated. And we might remember that a few years ago, there were some false detections of things like, something had gone faster than the speed of light or something.
Oh, the neutrinos, yeah.
Yeah, and it's like, no, they didn't. It was a mechanical error, and it was absolutely vital to have the instruments so finely calibrated that they could pin it down and reproduce it. And the reproducing of the observations was one of the reasons why they actually trying to get multiple detectors, and there are now several. But LIGO had, as you might imagine, with something that took 21 years to materialize, several dangers of being canceled. And that's actually when Barish, a former particle physicist, he stepped in to kind of lead the project to completion, and was a major driver behind actually pushing it over that finish line. And the full vision of this being something like a 50-year process by literally thousands of people to make a confirmation that was predicted by Albert Einstein 60 years earlier. So it was an amazing point in time, and the LIGO detector, it's a laser interferometer gravitational wave observatory, just in case anybody wants to know the full name. So, as with many things in astronomy, we love acronyms. But yes, it can be found. I believe they do have a visitor center, but I can guarantee you will not be able to actually go and touch any of the lasers because they're very, very finely calibrated. And right now in North America, there's both LIGO Hanford Observatory and LIGO Livingston Observatory. And the more locations that they make on Earth, the more confirmation they have of each detection. Because the way that gravitational waves work is you actually can make your observatory pretty much anywhere on Earth to get that detection. It's really, really cool. Amazing time in astronomy history, physics history, engineering history, and probably something else as well. So a big shout out to 2017 and LIGO detector.
Absolutely. I remember October 3rd, 2017 was a month after I had started going to school at York. And it was all anybody in the physics program was talking about. This was huge news. And what I find so interesting about the LIGO experiment in particular is it's such a reminder, as you mentioned, of the necessity for patience and perseverance in physics, because just because you haven't discovered anything yet doesn't mean nothing's happening. It just means that more work is necessary to achieve that final result. And it's also a reminder, I think, of the fact that even though the award was given to 3 people, that science is a collective effort, and it took a team of thousands to make all of this come together. And without that team, none of this could have been possible. So I think sometimes we get this idea that like science is carried out by a few geniuses who just are able to have these insights that nobody else could. And well, it's certainly true that we owe a lot to particularly great the insights of particularly great people. Most science is carried out by large teams of researchers who are all contributing to the project and who all deserve credit for that contribution.
Yeah, and that is why you will see that a lot of collaborations have made bigger efforts to include the authors' names on their publications, and we do have some very hefty ones now. But I vastly prefer that to 2 people and then leaving off the other 20. And as you say, it's currently there are still over 1,000 scientists involved in conducting LIGO research, and they're members of the LIGO sort of collaboration consortium. But they've got hundreds of students, thousands of scientists, and if it wasn't for all of these people working together and actually being able to share data, results, and ideas, this is why communication is a huge science skill.
All right, should I move on to the next point?
Yeah, so speaking of communication,
absolutely.
Quentin, I'll use this to send it over to you, and I believe you're going to go back in time a little bit.
Yeah, so I'm going to go back 2 weeks, I believe, 2 weeks and then several hundred years. On September 23rd, 1846, the planet Neptune was officially discovered. So the French astronomer Alexis Bouvard had published astronomical tables on the orbit of Uranus in 1821, but later observations demonstrated that the planet's actual position differed substantially from what the tables predicted. So this prompted Bouvard to suspect that another massive object was perturbing its orbit. And beginning in 1843, John Couch Adams, working with the Astronomer Royal Sir George Airy, published estimates of this unknown body's longitude. Urbain Le Verrier, independently of Adams and Airy, was also working on his own estimates at around the same time. And when Airy saw that they were quite similar to the figures provided by Adams, he persuaded James Challis to attempt to observe the planet. Challis did observe the planet on 2 separate occasions in August of 1845, but did not recognize these observations as a new planet until he was analyzing the data later. And by this point, Leverrier had already asked Johann Friedrich Gall to perform his own search for the planet, which he successfully observed on September 23rd. So Gall is considered the official discoverer of Neptune, but as you could probably guess, the question of who really deserves the credit was a controversial question at the time. Interestingly enough, however, Galileo actually observed the planet more than 2 centuries before any of them, in some of the first observations ever made with the telescope. Some of his drawings from 1612 and 1613 contain plotted points which line up with where Neptune is known to have been on the dates they were drawn. However, Neptune had only recently turned retrograde when these observations were made, and therefore would have appeared nearly stationary in the sky. As a result, it is suspected that Galileo may have mistaken the planet for a stationary star. But even this has been called into question lately, as some details in Galileo's notes seem to suggest he may have indeed noticed that this star had moved with respect to the background. Turns out, the question of who discovered Neptune is actually really complicated.
Yeah, this is another great lesson from history, really, because a lot of times people do discover things over and over again, and especially early on in 1600s, 1500s, anytime around that, communication was not what we have today. It was very difficult to share information, from example, from Europe to China or to other countries. We didn't have the great amount of sort of just post it on the internet and then click, translate that we now have for scientific articles. And so it's no surprise that Galileo could have found the same thing that everyone else found, and he might not even have been the first. There are evidence of some very, very detailed observations from early China and early India, and who knows. But we can say that it was predicted and then found, which was really quite interesting. And that finding something that doesn't fit, looking at the planet's position and realizing that it's wrong, and then trying to explain that is a wonderful example of a scientific method of, okay, what is this? This doesn't look quite right. And this is, of course, how Kepler ended up with elliptical orbits. And it's, letting the data speak for itself rather than what you hope it will do. So I think it's a wonderful, wonderful discovery. And whether it was discovered before or not, it's absolutely amazing that they actually were able to work backwards from calculated positions and predict a true extraplanet.
Absolutely. It's a scientific method in action.
and the way it was done was very nice, I have to say. And Neptune, of course, being critically important for understanding that icy outer solar system, and it's just it's really a shame we haven't done more exploration of Neptune. I'm really hoping we get a Neptune mission at some point soon.
Absolutely. Well, we'll add it to the very long list of exploration missions that we really want to see happen.
Yes. Well, Neptune and Uranus are pretty sparse in terms of space missions, but I suppose we could make arguments for lots and lots of extra missions to the moon Triton as well. It's just a fascinating place.
Absolutely.
All right, so Neptune, very, very fun stuff. I'm hopping around a little bit, so I'm sort of going back and forth in history here. We didn't necessarily set our dates in order, but speaking of discoveries, we've been talking a lot about optical astronomy, and today in 1931, so substantially after the discovery of Neptune, we actually had the first radio telescope. Karl Jansky and an engineer at Bell Telephone basically came together to invent a radio telescope. And this is a pretty fun little story as well, because the history of radio astronomy is really quite interesting. So radio astronomy really evolved strongly basically around the end of World War II. Radio was a very important tool for communication. It bounces around just right through the atmosphere, and it works very well for sending signals on Earth over long distances, much better than cables, because cables only run where you have the cable. Radio waves can travel through the air or space or anything. It's just another wavelength of light. But radio astronomy, comes about because of the developments of previous scientists before. So this was, again, not a single person just inventing radio astronomy. We had scientists like Faraday and Volta performing experiments with electricity and magnetism, people trying to figure out that charge carriers were negative, and of course, James Clerk Maxwell in 1879 getting that theory of the electricity and magnetism coming together to make light, and electromagnetic waves. So radio's waves are electromagnetic waves, and realizing that they're just electromagnetic waves at a different wavelength. It was Heinrich Hertz who actually built the first radio wave transmitter. Today we call these LC oscillators, and just like Maxwell's theory predicted, the waves are polarized when they come out. So you had all of these people running around playing with radio waves, electromagnetic waves. You have Max Planck in there doing his experiments with quantum theory. Of course, Albert Einstein, Louis de Broglie, and Erwin Schrödinger. And so you have a huge number of people coming in, not to mention, cannot forget Giuliano Marconi, which I'm probably saying the first name of wrong, who basically was the first person to send and receive signals across an ocean from Newfoundland to Cornwall. So we had all of these people developing radio, and radio astronomy, however, came about because people were using radio, and they figured out they could send communications with radio. And they started to notice that they were having some trouble with their radio communications. So the study of astronomy actually came about because radio communication on Earth was getting some interference. And this was all the way back in the 1930s. So I started off this story in the 18 or 1700s or earlier. So 100 years later, we've got people on Earth using radio, and the Bell Telephone Company was having trouble with their transatlantic service. There was some sort of static on the line, some sort of interference. And they asked a physicist, Karl Jansky, find the source of the interference. This is bad stuff for us. It's interfering with our communication. Find the source of this interference. And so he actually tried to track and identify the source of whatever was causing this interference in radio transmissions. And he built a big rotating antenna, which looks a lot like just a big wire. And it's sort of these early antennas were literally just wires strung between poles. So they kind of look almost like clotheslines, mini clotheslines stacked together. But wires are able to pick up radio, as all of us who have antennas know. And this was built on a rotating platform and given the name Jansky's merry-go-round. And it was designed to receive radio waves at a frequency of 20.5 megahertz. So it would rotate around and it would try to locate the direction of the radio signal. And it's pretty cool. If you can find any pictures, it looks extremely unstable. It really does look like somebody just put up some large poles and put some wheels underneath them. And Jansky spent months studying this static. I believe it took him a little while, but he was able to classify it into 3 types of static. So 1 and 2 were nearby and distant thunderstorms. So thunderstorms and weather on Earth actually do generate interference. But there was a 3rd source of static, and this is where radio astronomy begins. The 3rd source of static was different somehow. There was a pattern characterizing the static wave signals. It was similar to the known location of the sun, but after a few more months and lots of accurate measurements, the things that scientists love, he found that the signals repeated every 23 hours and 56 seconds. So, I mean, we can think, okay, well, what happens every 23 hours and 56 seconds? We spin around. We have a day and night in the Earth spins. And he's like, okay. So he actually narrowed it down in this method with this very ungainly contraption and found that the radiation was coming from the constellation Sagittarius in the Milky Way galaxy. It was coming from the sky, and not just any part of the sky. It was coming from the direction of the center of the galaxy. And this was really where people got very, very interested in radio astronomy, because they said, what? Radio signals from space? 1911, big news. So this motivated a lot of people, but very importantly, it motivated Claude Reber, who was a radio operator and engineer, and he went to apply for jobs with Carl Jansky and Bell Laboratories specifically to investigate radio waves. He wanted to find out what process was there and really investigate it. They were substantially hampered because this was actually during the Great Depression in the U.S. and there was not really any funding. Bell Labs were not hiring. So Reber at this point took over and basically did it from his backyard. He constructed a telescope, and he actually constructed the first dish radio telescope to figure out what this radiation was in his backyard. So this discovery was pretty awesome, and it all got started off with October 3rd, 1931, and Carl Jansky. So we could probably talk quite a lot more about the radio telescopes, but needless to say, if you like radio and you love Fourier transforms, radio telescopes might be for you.
I mean, if you're listening to this, you clearly do like radio, so that's at least one of the two.
Exactly, yes. I hope we have some radio interested listeners out there. Indeed.
Should I move on?
Yeah, I think let's go ahead and do your next. Let's move onwards and upwards. And actually, your next item is around the same time. So mine was 1931. You're just going to go back a few years. So take it away, Quentin.
Yes. So on September 20th, 1910, Dorothy Vaughan was born in Kansas City, Missouri. So Vaughan was a mathematician and computer who worked for NASA and the National Advisory Committee for Aeronautics, NACA, from 1943 to 1971. So during those days, computers weren't machines. They were human beings who were employed to carry out long mathematical calculations. These workers only really started to be replaced with electronic computers at a large scale around the 1970s, and many of them were women, especially during times of war like the 1940s. Vaughan began working as a mathematician and computer at Langley Research Center during the height of the Second World War. And due to the prevailing Jim Crow laws in Virginia at the time, she was required to work in a segregated unit composed entirely of other black computers. In 1949, she was appointed the acting head of the unit, the first black supervisor at the NACA, and one of only a handful of women who held the role. She served as the acting supervisor for several years before she was finally promoted officially. She pushed for opportunities for women throughout her time at the NACA, both within her department and outside of it. She would later remark on her time as an African-American woman working at Langley, "I changed what I could, and what I couldn't, I endured." The NACA became NASA in 1958, at which point the segregated facilities were abolished and Vaughan was no longer required to work separately from her white colleagues. A gifted computer scientist, she taught herself and her coworkers Fortran in order to prepare them for the transition to machine computing that she anticipated on the horizon, which began in 1961 when the NACA introduced its first set of digital computers to the center. She worked on the Scout rocket program, for which the first successful launch occurred in the same year. Unfortunately, she never received an offer to occupy any other management positions at NASA prior to her retirement in 1971. She passed away on November 10th, 2008, at 98 years old. She was one of the women featured in the book Hidden Figures about the contributions of African-American women to the space race, which was adapted into a film in 2016. She also received a posthumous Congressional Gold Medal in 2019. The Vaughan crater on the far side of the moon is named after her, as is the NewSat 12 Dorothy Earth observation satellite, which was launched in 2020.
An amazing, amazing person, and yes, happy birthday. We were all lucky to have her at NASA for sure, and I just would say, teaching Fortran is also a very noteworthy feat because that is not an easy computer language to work with.
Absolutely not.
It is substantially more difficult. So if you've had any experience with Python or Java, you can indeed count yourself very, very lucky. She was a incredibly smart, incredibly capable woman who did an amazing work, and I'm so pleased that she is finally, unfortunately posthumously, getting more recognition today.
Absolutely.
All right, so I guess next time you see those far side of the moon pictures, see if you can find that Vaughan crater. All right, so let's see here. I've got one more. I think I'm going to go ahead and take this time really quick to just remind everybody, you are all listening to York Universe, broadcasting live from the Allan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. If you have any questions or you're trying to find the OPV online public viewing link to join in the live chat, hop on over to observatory.info.yorku.ca. We have also lots of posts on Twitter at YorkU Observatory and Facebook at Allan I. Carswell Obs. Tonight you're listening to Elena and Quentin, and we're currently discussing This Week in History, and we just got done discussing Dorothy Vaughan and Vaughan Crater. It is a lot of fun out here tonight, and hopefully you all are getting some of these amazing clear skies that we seem to have both at Killarney and downtown Toronto. Amazing. All right, so let me go ahead and take us really quick back in history for one last little This Week in History, and then we'll move on to some fun reminders and news items. So I have just one more, and it's a little bit of a blast from the past. You mentioned Galileo, I think, Quentin. Well, it was actually October 2nd, 1608, that not Galileo, but Hans Lippershey submitted the first recorded patent for a refracting telescope. So we talk a lot about things being invented at the same time, what is commonly called the Galilean Telescope. Well, it did actually have a previous patent. Hans Lippershey was a German-Dutch spectacle maker, and he did actually file a patent before Galileo had any use of telescopes. It's unclear if he was the first one to build it, and it's worth mentioning that at this time, the patent he filed was in 1608. There was quite a boom on optical devices, spectacle making. Glass had become something that could be refined and created and dealt with in a different way. And manipulating glass, making lenses, had become into somewhat, in fashion. You could actually buy optical corrections if you had poor eyesight. You could have convex and concave eyepieces. So it was really only a matter of time before someone put them together. And he might not have been the first, but Lippershey did file a patent. And it's actually quite interesting. He wrote the earliest written record for a refracting telescope. The refracting telescope is the one that you see in those historical pictures that's very, very, very long. It has a very long tube, and that's because it uses not reflection from mirrors, but it actually uses a lens as its objective to form an image. This is sometimes also called a diopter telescope. The refracting telescope design can be found in spyglasses, and your old-fashioned pirate glass that you can look out on the seas with, a big version of that. Astronomical telescopes were, when they had this first refracting design, basically just very, very, very long, big spyglasses that were anchored firmly to the floor. And the anchoring to the floor became realized as very important. But the refracting telescope design is also used for long focus camera lenses. It's a very popular design, and it's pretty easy to make a reasonably good lens. It's a lot harder to make a perfect mirror, and the technology for that is a little bit different than lens and glass technology. So these long tubes would have a lens at the front usually, and then eyepieces are instruments at the rear when the telescope image comes into focus. And that long length is to bring it into focus so that you can perhaps get a picture of it maybe, or draw your observations. So this was a attempt at a patent. It was unsuccessful, actually. He filed the patent, and I believe the patent was quoted as "for seeing things far away as if they were nearby."
Very descriptive.
Yes. So that is the official patent filing with the States General of the Netherlands. However, this was only a few weeks before another Dutch instrument maker's patent. So Jacob Matthias also tried to file almost the same time, just a few weeks. So he failed to receive the patent since the same claim for invention had been made by other spectacle makers. And again, this does make sense because if you've got concave lenses and convex lenses, it's only a matter of time before you realize you can put them together to make a pretty good magnifier. He did not win the patent, but he was handsomely rewarded by the Dutch government for copies of his design. So he did still managed to come out relatively on top for this. And his application was mentioned at the end of a diplomatic report on an embassy to Holland, which is the Netherlands, from the King of Siam. And this, report has since then gone around. But at the time, it was Galileo Galilei who was very, very interested by this patent. And Galileo, of course, would then take the invention of the telescope and make quite a few little improvements to it. So he refined this idea of using a lens, and he first, of course, heard about it because it was making the rounds in 1609 and went to make a copy for himself. So he said, okay, I'm going to make one of these. And the first telescope Galileo made was about a 3 times magnifier, which is not great, but it'll bring out a little detail. And Galileo continued to refine and develop his refracting telescope until he had about 10 times magnification, which would allow him to see things that had never been seen before, high detail on the surface of the moon. Of course, the moons of Jupiter, some of which were actually listed as having been discovered by Chinese astronomer Gan Day in 364 BC, but all 4 moons were very well documented by Galileo. So even the Galilean moons have more discoveries behind them than you might think. So obviously Galileo would get into quite a bit of, go ahead.
Yeah, I was just going to say, isn't there like a common saying in science that everything in science is named after the second person who discovered it?
I haven't heard that. But I mean, in this case, Hans Lippershey even filed a patent, and he couldn't get the telescope named after him. But he might not have been the first one to make it. So it's very true that it's worth thinking about all of the people who are involved behind these discoveries, because if you didn't have this optics boom, if you didn't have Hans Lippershey and his colleague Jakob Matthias, if you didn't have all of these people, then that idea would have never reached Galileo, and he would have never tried to build one himself, and might never have discovered the Galilean moons for himself. And the fact that some of them already were discovered quite a bit earlier, it is iterative. It's very fun stuff. But yes, it is often the case that the person who has it named after them it's not the single scientist myth, right?
Yeah, I mean, it never is, right?
It's very rarely. I cannot think of a single case where it really has been just one person, but it could be because it's getting a little late. So let me go ahead and take this opportunity just to remind everyone, actually, with the recent amazing Nuit Blanche success here at York and the Stars over Killarney for our astronomer in residence, we actually do have in-person viewing this October 8th, which is not a Wednesday, over at York Observatory. So if you want to find those Eventbrite tickets, they are online available for free. And I think we have time for probably one news story. Which we have been having too much fun here tonight talking about all the fun stuff in history. So Quentin, shall we cover DART or Saturn? Or
let's please cover DART. I've been wanting to talk about this all day.
Okay, yeah, me too. So for our news item today, there are so many amazing things happening right now in space. We had, a flyby of Europa by Juno. We've had, the MOXIE producing oxygen on Mars. We've had, Saturn's rings being analyzed, but nothing beats watching the double asteroid redirection test DART actually slam into the little tiny little tiny asteroid. So this was, I'm getting too excited. This was a bullseye in space. There was a 1,300 pound small satellite which was launched, and it actually launched itself a CubeSat before impact. It was going 14,000 miles per hour, and its goal was to change the orbital speed by a fraction of a percent due to kinetic impact on a binary asteroid system. This was Didymos, who was the main asteroid, and Dimorphos was the smaller asteroid. So Didymos was about half a mile. Dimorphos is more like 160 meters. Very, very small rocky objects. And they're very, very far away, so there's no chance at all that they would ever impact Earth. And by hitting the small one, they hoped after impact that it would go about just a little bit faster and shorten its orbital period. So they impacted it in such a way that they hope that they have shortened its orbital period. And this little nudge means that we can now watch it. So this telescope, the Earth-based telescopes all over, and unfortunately, on the night that they did this, it was cloudy, so we couldn't watch. We couldn't watch. We were all ready to go at York, and we couldn't watch it. But other telescopes did get pictures. So the debris cloud that was kicked up was pretty substantial. It was visible for several days, watching that sort of debris now in orbit around in the binary asteroid system. And it was actually, the impact was also monitored by the CubeSat that they let loose at the last minute, the Italian Lycia CubeSat, about 3 minutes behind. They have a debris cloud. They're wondering how much impact debris is going to go to Didymos. Is it going to affect its rotation? Is it going to do what they thought it was going to do and shorten its orbital period? So we're going to now have to watch this system with all of our telescopes. It will take a while, and over the next 2 to 4 years, we can actually really finally qualify exactly how much this impact, this kinetic impactor, was able to move this binary asteroid system. Is it going to affect the whole system, or is it going to just shorten the orbit of the one? It is really exciting. So if you haven't seen the video, I highly, highly recommend it. NASA.gov, DART, I believe there's an in-depth article that you can find that is pretty comprehensive. Double asteroid redirection test. And the great thing about the video as well is that as you're watching it, you see absolutely nothing up until the last few minutes, when the tiniest little dots start getting larger and larger and larger, and then the screen is filled with those rocks getting nice and close up, and it goes black. So this launch was fairly recent. Or the launch was a little bit ago. The impact was fairly recent. So it launched on November 23rd, 2021, and it did take quite a while to get there. 6.8 million miles from Earth, the system, and nice and far away. Impact on September 26th, 2022 this year. So you can still find the mission status page. It's been active for 10 months, 1 day, 12 hours, 53 minutes. Very, very exciting. And we have a lot of pictures very close up of before the impact from Dimorphos. And afterwards, we have some lovely, lovely pictures from ground-based telescopes watching the debris cloud and watching the orbit. So if you love orbital dynamics and binary systems, this is going to be a really fun one to watch.
Absolutely. I can't wait to find out what we learn from this. Basically, any kind of information from this is extremely helpful.
Exactly. And it's you might have heard of movies like there's a Deep Impact and the big Hollywood blockbusters. What are we going to do if something's going to hit Earth? Blowing things up is really, really hard and also problematic. But redirecting them, that we might actually be able to do. And this experiment was the first one that was actively trying to do redirection. We have crashed into things before, but with less purpose or for different reasons. this was the first time we were actually trying to redirect, and it would be pretty awesome if it does work. So I'm afraid we are going to have to close up there. It is super, super fun, and we've had a great time being here tonight. Everyone, you have been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Quentin and myself, Elena. Stay tuned because it is Astronomy Night in Canada. Coming up next is Quirks and Quarks, Western Worlds, and Science for the People. You can always connect with us on Twitter at the handle York Universe, and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in to York Universe, clear skies, and have a good night.
Have a great night.
Program from AFM Radio, the broadcast service of Astronomy.fm. This program has been released under Creative Commons license. Please